sense of the kinds of topics that people in the other program are looking at. And I think so Mukund, who's from the University of Durham, has kindly agreed to give a short kind of overview. And I guess the idea is that people can, it's very, very informal, so the idea is that people can ask questions. If there's particular topics that people are interested in, they can ask about that or try and spark some discussion. And basically it's up to us kind of what we cover. So feel free to interrupt it, of course, like more than usual in terms of asking questions, because this is meant to be designed for quantum information people, and there's going to be language barriers, so ask lots of questions.
Thanks. So when Jonathan asked me to do this last week, I said sure, and you know, the title has the word tutorial, and after being in Durham for 8 years, I associate the word tutorial to mean do nothing, just show up. So, so I have very little in terms of actual material that I have prepared, so I don't really want to make this into a seminar. I'd much rather you folks ask me. So I'll sort of set the stage by saying a few things, and then I'd much rather have you guys ask me, you know, okay, can you elaborate on that, or is this something that we should think about, or so on. So we could, I'd much prefer that this be a discussion forum rather than my talking on for an hour. So, so just to set the stage, I want to give you a flavor of how I think about holography. And more generally about this statement of connection between gauge theories and gravity/string theories. And I promise you that the word string will appear just this once. I won't actually use any string theory to motivate the gauge gravity correspondence. So let me start with a very simple system. Let's talk about a system, Hamiltonian system.
You might even have to explain what a gauge theory is.
I will.
Right, because some of us are really from
right. So let me step back and let's talk about quantum mechanics.
Yeah.
Right.
Okay.
So let's talk about quantum mechanics for a system where my basic variable is an n by n matrix. Okay, so matrix quantum mechanics. So I have some matrix M, and we could sort of write down some Hamiltonian for this matrix. But really what I want to talk about is not just the matrix itself, but the observables that I can build out of this matrix. Okay, so this matrix is like a basic alphabet. And so I can build words from this matrix, which are things like, if I have a single matrix, I can build words which are I can take products of this matrix and take a trace to make something that's invariant under the matrix rotations. I can make, so these would be sort of, in my language, simple words. And we could make composite words or hyphenated words, which would involve multiple traces. Right? So these certainly are observables, and one thing we can do if you're doing matrix quantum mechanics is to try to figure out a way to compute correlation functions of these words. Right? We can sort of insert these into our talk about pick some state, say the vacuum state of the quantum system, and then compute the inner product of states obtained by hitting these words on the vacuum.
Are you assuming M is self-adjoint or anything about?
Yeah. So for now I haven't said anything, but let's say this is going to be a Hermitian matrix for definiteness. So eventually I want to sort of take this quantum system and upgrade to what I call a gauge theory. And the only point I'm going to use in the gauge theory description is that the basic fields of my gauge theory are going to be matrices of this kind. They're going to be Hermitian matrices, and the observables we naturally talk of, the local observables we talk of, will be these kind of words.
So do I think of M as a single matrix or as a set of matrices?
So for the purpose I started with, it was a single matrix, but in a moment we will generalize. So you can think of M as a collection of matrices that show up in your quantum system.
Are the exponents supposed to be positive integers?
So in the context I'm talking about, they are positive integers.
Why are these observables? To me, why you consider trace not just some like average value in some state?
So these are observables in the sense that these traces, these are operators. These are operators on the Hilbert space, and their expectation values are what I will call observables. So in the gauge theory language, these are the local observables that one can use to sort of measure local quantities in our gauge theory.
But normally observable is an operator and you take average value, and this already, where you have state here?
This is an operator. This trace is a matrix trace. I haven't sandwiched it between any states.
You haven't, yeah.
Yes.
So, where do this trace? I don't know.
Oh,
Understand?
okay. So
No, people understand me, but I don't.
You understand?
okay. All I mean by this trace is this.
We'll insert the state after.
I just want to sort of take the matrix.
The
state.
number.
It's a
Mn is a number, yes?
no. M is an operator. In
Yeah, but trace Mn is already a number.
No.
No. Aha. So there's some special relativistic trace. Yeah.
no. M has indices, right? The trace just I cyclically string through M matrices, and then contract the indices.
Confusing bit is taking a trace of a single matrix by adding the stuff on the diagonal versus, taking.
Okay, so for me the entries of M are operators, right?
Entries of M.
Are operators.
So you're,
No, it's the plasma trace.
They're not scalars. No.
Okay, I was just thinking of a
This is okay.
sigma Z matrix as a typical Hermitian matrix.
That's the point.
so we're working in operator spaces.
I'm strictly working in operator space. We're not talking about matrix elements in any state. We talk these. I haven't talked about matrix elements at all. Right.
And so your trace is basically the sum of the blocks.
Correct.
Great.
Correct. So when I want to talk about matrix elements, what I really want are things like this. Okay, now I might put some state here. Let's just put some quantum state of our matrix. So these are my observables. Okay.
For the sake of clarity, can you actually define the trace on the board as well?
It's a standard matrix. I have one. So in this case, I have one matrix. Let's say it has.
Those B's are not exponents, they're the different
They're the components.
indices.
Yeah,
That's a relativistic way of writing it. We usually write it both as a subscript.
Yeah, I mean,
the word relativistic confuses me. I associate the word relativistic to be something completely different.
In general, the style of writing tensors in general.
Yes.
I mean, isn't
Summation convention is.
Do write down the definition. I think it will help.
Yeah.
well, that's confusing.
Okay, now I think that's the sum of the block of the diagonal block.
So it's a partial trace for us. Thank you.
Except that the
no,
things
but-
in the matrix elements might not be matrices, they might be operators on an infinite dimensional space.
Yeah.
This is a matrix of operators.
Yeah. It's like
operators.
it's like CD test or something, and we trace this CD card.
So here's trace M cube, for example.
That's more confusing.
Isn't it perhaps easier to first explain gauge invariance and then demonstrate that
But this is why I went further behind and talked about quantum mechanics.
I think we're there.
Good? So far so good? Okay.
So what, I'm afraid I don't understand those indices there.
Oh, sure.
Okay, good.
Instead of using eight subscripts for the blocks, you use a subscript and a superscript.
Yeah.
Would this help?
Yeah, okay.
And you have the summation.
Summation of
You have to write the summation.
This was figured out by Einstein, right?
Okay.
Everything about the summation.
You know, I insist that we teach summation convention to first year students because I never like writing explicit summation labels. But
Then what do you do if you don't have a sum?
then you just leave it dangling, right? So if I want,
I mean, how would you
No,
come
but
up
that's-
with diagonal elements of
Okay, let's-
Can I suggest you move on?
Yeah, we move on. Yeah. You already understand it.
all right. So
Yeah.
so this is in the quantum mechanics theory, but I could imagine sort of talking about many body systems or quantum field theories where these objects, these matrices would depend not only on they not only be operators, but they would be position dependent operators. They could depend on space-time coordinates. Okay, so we could talk about where x now refers to all of space-time coordinates in whatever dimension we are in. Let's say we have 4 dimensions, then this x could depend on the 3 spatial and 1 temporal coordinates. So I'll just use one label for it.
So that's each
At every point,
element in the matrix, what I was thinking of as a scalar is
Yes.
now an operator that depends on
that's right.
continuous spatial space-time coordinates.
Correct. So I have a collection of n squared. If M was an n by n matrix, I have a collection of n squared operators which have assembled into a matrix, and they belong, and they depend on the spatial vector. Now, the operative point is that if you want sort of to talk about these class of objects in a gauge theory, these matrices are elements of, let's say, the algebra. They could be elements of SUN, and I'll view this n index n, which is a integer label, as a parameter I can tune.
SUN is this is a representation. So where you have this now? So now these are standard matrices. Yes.
These are n by n complex matrices.
So now the elements are scalars.
The elements are still operator valued.
But they're now unitary.
They're now unitary.
The elements.
The elements are
So not M is SUN, but elements of M.
M
And like
of X.
NAB is belongs to SUN. Yes.
correct.
Entries.
So these objects that I wrote down, we can still compute them in this gauge, in this quantum field theory. So this is some local quantum field theory, and so the question is, we need a computational scheme and now I have generalized. I'm going to generalize. I'm going to allow myself more than one matrix. And I want to compute these kind of observables. Okay. Now, of course, these are going to depend. So if I call these my simple words, if I denote this by some O1, denote this guy by O2. In this generalized story where I have made my matrices depend on space and time coordinates, these operators are also functions of space and time, and we could insert them at different positions in space and time. Okay. And this we need some, so we would like to sort of be able to compute this, and so the usual rules of one can sort of come up with usual rules which sort of take the usual ideas in quantum mechanics and try to implement them in this local description in quantum field theory. But something nice happens, which was noticed long time ago, which is why I bring this matrix model up. by 't Hooft, that if n, this rank of this matrix is large, or more specific, let me take n much larger than 1, then there is a big distinction between these simple words and composite words. The composite words in a rough sense decouple, and you are left with only the simple words. Okay. This is not true at any finite value of n, but in an asymptotic series in a 1 over n expansion, the composite words simply sort of decouple from the system.
You mean that expectations are independent?
Exactly. So in fact, you can say a much stronger statement. These kind of expectations that I write down of these words, they factorize in the large n. So this becomes, if I had just 2 of these, okay. So the expectation value of these operators, which is a complicated function, starts to factorize, and this is true up to order 1 over n corrections in this large n.
Just for the audience.
Yeah.
The reason that you have a difficult idea is that quantum chromodynamics, that stuff is quarks and gluons, out of which protons and neutrons pop up, has precisely the structure for n is 3.
Correct.
Right? And then you find out that the large n limit has these simplifications.
Yes.
The relevant n is only 3.
That's right. So as Jan said, this was motivated for 't Hooft by physically trying to understand strong interactions, quantum chromodynamics. But the formal structure is true, and we don't really need gauge invariance for that formal structure to be true. This is true already in this matrix theory without any of this enhanced quantum field theory baggage. So this factorization property is important, and the key point is because of this factorization, the quantum correlations between these simple words is much simpler than at infinite n than you would expect at any finite value of n.
This is under some condition on the state,
So these are correlations computed in the vacuum,
which is
so sorry.
Sorry, how do you define vacuum?
I define, so we could go through the exercise. I could split up M into creation and annihilation operators, and the vacuum is defined as usual by declaring that all the annihilation operators annihilate the vacuum.
So it's a free theory?
It's not. It doesn't have. So this statement is true even in a non-free theory, but
then the vacuum is not.
The vacuum is some complicated. Yes, but this factorization comes not because of the structure of the vacuum. It comes because of the way these interactions work in this 1 over n theory. So in some sense, the interactions in this large n theory are order 1 over n.
For any state, not only for the vacuum?
For any state, yes. So a better way to say it is that the large n theory is effectively classical and the effective Planck's constant is proportional to 1 over n. Okay. So this factorization happens. One can argue this in general. If you ask me why is this true not just for the vacuum but for any excited state, most excited states I can think about by acting on the vacuum with some other set of operators. So I can bring back all correlation functions of any kind of in any excited state to a vacuum to vacuum correlator, and the factorization holds in that vacuum to vacuum correlator. So there is this classical theory, and the question is, what is it? So I started with a theory of matrices, and I told you that if I took the rank of my matrices very large, I made my theory effectively classical. So what is an effective classical Hamiltonian that describes the dynamics in this large N limit?
If you're going from the vacuum to some other state, you say it's because that may not, will you always be able to deal with the product of operators?
Yeah, so I can make the other state is with the product of operators. So
I think they are low energy states because if you have order n particles, then you.
Thank you. So there is some order of limits involved. I should sort of not make my states with too many particles, because then the factorization will break down. Right. So or in particular, I also was very glib when I said about these composite operators breaking decoupling. That can only happen if with the relative normalization of the trace being consistent. If I sort of start scaling up this trace by n, then the composites won't decouple. So I can put coefficients here where this composite operator has an extra factor of n relative to the simple operator, and then I might keep the composite operators in my theory. So indeed, so in the simplest sense, there is a way in which this works, but we'd like to know what this classical theory is. So for a general theory, we don't know what this answer is, but for a class of quantum field theories, so what I mean, my notion of large N theories is precisely this class of matrix-like theories where the fundamental objects are built out of matrices. This classical theory is a gravitational theory in one higher dimension. So let's say my matrices theory was in 4 dimensions, and for me 4 is 3 plus 1, so 3 space and 1 time. Then the classical description is a 5-dimensional gravity. Okay, so this is an answer that comes out of a long story. I'll tell you where the story answer comes from, but this is the sort of, in a nutshell, the statement of this gauge gravity correspondence. So there's a sector of this matrix-like theory which is effectively classical, and that classical description is not captured by matrix degrees of freedom. It's captured by a completely different set of degrees of freedom that interact by a gravitational Hamiltonian. Okay.
It's worthwhile to emphasize here that when you look just at your original field theory and sort of normal H bar terms and so forth,
yeah,
right? That theory appears as extremely unclassical in a normal sense.
Well,
just the encoding, right, in the one higher dimension, the gravitational dimension, where the classicalness resides.
Actually, no, I disagree. This factorization tells you that. Yeah, this factorization tells you that even in the.
I agree with that statement.
Yes.
But when you're used to, real classical theories,
yeah,
right, these things look very, very different from these real classical theories. There is a sense of entanglement and so forth in terms of normal coordinates.
They're strongly coupled.
They're strongly coupled.
Yeah, but
extremely complex mechanical theories. When you look at it, there's somebody who's trained to look at the math.
Yeah, I never used the word strong coupling. This could be string theory. I just said gravity theory. I didn't say what gravity theory it was. It could be classical string theory.
Matrix theory.
No, it could be a free matrix theory. This would not be a complicated gravity theory. This would just be classical string theory. So the only point I want to make is that there is a classical description.
I agree with you. I would more like don't give the people wrong intuition, because the kind of field theories you are describing this way are extremely wild and with things that doesn't look like anything that's truly classical. This room is intuitively truly classical. Just alluding to that intuition.
Yeah, I think we're not disagreeing with the statement, but I think there's slightly different intuition of what we mean by truly classical.
It's semantic, what is classical.
Yeah. So that's the statement that comes out. So I'm not going to try to derive this statement. Deriving this statement would take me into, well, I don't know if we know how to derive this in general, and in a particular class of theories we know the answer from certain manipulations in string theory. But let's take the answer for now and see what we can do with it. So, I mean, I should note that, by the way, that this 4-dimension wasn't special. We could sort of do this even at the level of the simple matrix quantum mechanics model I have, and there is, even in the context of matrix quantum mechanics, a simple dual in terms of some effective classical theory for even the free matrix quantum mechanics. Okay, it's not a very simple gravitational theory, because that gives you a gravity theory in 1 + 1 dimensions, time plus 1 extra direction, and it's a more complicated gravity theory than what we know in our universe. But one can certainly write down such gravity theories. So let's see. So let's take the matrix theory, the matrix gauge theory in 3 + 1 dimensions, and let's ask that this theory be critical. Let's say this theory has a so in particular this means that this theory is scale invariant. So these days I don't need to say this, but okay, so the 4-dimensional theory has some enhanced symmetry. It's invariant under local changes of length scales in my 4-dimensional theory. Okay, so these theories exist, and I'll pick one of these. And I need this strongly coupled to simplify this classical gravity description, this classical description. Okay, so the strong so we talked about what kind of coupling there was. So there's one notion here of an effective h bar, which is 1 over n, but the intrinsic Lagrangian for my matrices M could involve additional coupling constants, which I could tune to be also large. And in this limit, if such a strongly coupled critical point exists, then the claim is the gravity theory is classical Einstein gravity. So the kind of gravitational physics we see in our real world, but relativistic, because the theories I'm talking about are relativistic, and the geometry of the vacuum of my matrix gauge theory is quite simple. It's completely determined by the symmetries. So let me motivate how this can come about without knowing any details of what the matrix degrees of freedom were doing, what the microscopic structure was. So, and the key point is the scale invariance. So let's say x is where my coordinates, so let's say I have 3 x's and 1 time, which is the four coordinates on which these matrices depend, But the vacuum state of this theory is scale invariant. So in particular, it's invariant under simultaneously rescaling all my coordinates in these 4 dimensions. Okay. So lambda is some constant rescaling of the length scales. Okay. So I want to write down some geometry that knows about this local rescaling, and in particular about this whole conformal symmetry, but it has one extra direction, right? So my statement was that not only do I have gravity, but I have gravity not just in the same geometry that I am propagating, but in one extra direction. And one can write down a geometry that satisfies this property. And let me just write down a formal equation. I'll explain what this equation means. So the way we describe geometry is by telling you how distances are measured, and here's an infinitesimal distance measure in the 5th dimension. Okay. So this is just telling me if I have points in 5 dimensions labeled by coordinates z, x, and t, the distance between them depends not on x and t but on z in this particular fashion. Okay. So I can encode this in a matrix if you want, but the whole point is that as I've written it, so this is an infinitesimal change in the z coordinate, infinitesimal change in x coordinate, and if I have neighboring points, this is the infinitesimal square length between those points. And there's a minus sign because I'm in a relativistic theory, so time gets treated separately from the rest of space. But the key point is that under local rescaling of these coordinates, this distance function is clearly unchanged. So what I built into this distance function is an encoding of this statement that there is scale invariance in my vacuum. Okay, and this geometry has a name. This is the anti-de Sitter geometry. And hence this statement, this connection between gauge theory and gravity is also called the area CFT correspondence, because the class of theories one is talking about have this conformal invariance, and that conformal invariance reflects in the fact that the vacuum state of the conformal field theory maps to this particular geometry, which is the anti-de Sitter space. Okay. So I'll draw one picture, but before I go ahead and draw a picture, do people have questions about what this statement is?
So n is large is very important for that, or not?
N is large is very important for that purpose, for me to be able to talk about a classical theory. Right? Because I told you that at large n is where this factorization of correlation functions happens. If n is not very large, I don't get a classical theory. It could be that I get a quantum theory in this geometry, but this geometry has dynamical gravity, so there's a quantum gravity theory, and so then we might be able to sort of talk about it in the context of string theory or so on, but it's not very helpful from the point of view of solving the field theory.
This means that the CFT dictionary works only in large and limit.
No, the dictionary works for all values of n and for all values of coupling. It's just that it depends on what your perspective is, what is it that you want to solve. If you want to solve quantum field theories, and you want to solve them by not doing too hard, by solving quantum gravity first, you're best off working at large n. Right? If you want to solve them by solving quantum gravity first, then we could be at small n.
Any example exist?
Sorry? Yeah, I'll give you an example. So there are examples of these class of theories. So. Any other questions? Okay, so let me draw a picture which is a bit useful. So I'll encode this geometry in a much simpler cartoon, which I think captures everything one wants. So one can think of a cylinder, a soup can if you will, and you can think of the matrix degrees of freedom living on the boundary of the soup can. Okay? So I have all these matrices that live on this boundary, and gravity propagates inside, and I think everybody has seen Escher's famous picture of a two-dimensional disk with these tiled by fishes or pigeons, whatever they are. Fish. And if I was in 2 + 1 dimensions, where I can draw this picture, Escher's disk has this geometry. The two-dimensional the picture of Escher's disk is precisely this geometry without the time, and the time just converts that Escher's disk, takes it up. You just stack up various Escher's disks, and that geometry you get is precisely this anti-de Sitter space. So gravity sort of propagates inside the disk, and we have our field theory living on this outer boundary of the disk. And this is one of the reasons why this correspondence is said to be holographic, that we have stuff that's sort of living on the boundary being described by dynamics that's happening inside, or vice versa. Okay, so that's the basic statement that one has from this correspondence, and I was asked for an example. So a particular example it has a name which is not important. It's called n equals for Soup-Yang-Mills, but it's more useful for me to tell you what the variables are for this theory. So I have matrices mu of x. There are 4 such matrices. So mu runs from 1 to 4. And I have 6 additional matrices, and these are the bosonic degrees of freedom, and all these matrices are elements of SUN. In addition, I have a certain number of fermionic matrices, which are also elements of SUN. Okay, so these are both these matrices transform, or these 10 matrices transform in the adjoint of SUN. Okay, so they have 2 labels with respect to SUN. So that's the gauge. That's the theory. That's a particular theory that has this kind of description in terms of gravity. And now I was going to sort of tell you a bit more about what we know about entanglement structures, but maybe I should sort of stop here to ask if people have any questions about the basic statement.
The S square, Z, X, T, where are these on this cylinder?
Thank you. So T runs up. So X in this picture runs along the circle, and Z runs inward. Okay.
So 2 is just X and T, and the third is Z. Yeah.
So the inside of the cylinder is parameterized by Z. Along the cylinder is parameterized by X, and if you have more dimensions, there are more X's. I can't draw them, and then time goes up.
So your initial theory was just on the bound on the.
Correct. My initial theory was living on the surface. It was like it was, and then the gravitational physics lives inside.
How we see that this Z is bounded because it's. Because this looks like Z is bounded from 0 to some radius. Where do you get this radius from?
Okay, so Z runs from 0 to infinity in this parameterization. So Z equals 0 is the boundary in my language, and then Z equals infinity is nothing special. It's just the origin.
And X is periodic, cyclic.
In the way I drew it, it's periodic, but
I would think of X. So if you do just a spatial rotation, you can rotate X into Z. What does that do to that?
Very good. So there's an obvious spatial rotation inside the X's. There's also rotations which exchange X's and T's, which are Lorentz transformations because this is a relativistic theory. And as you say, the rotations that mix Z's and X's and Z's and T's. The rotations that mix those are the part of transformations that are in the conformal group but not in the Lorentz group. The conformal symmetry is bigger than the Lorentz symmetry. Okay, and those are the symmetries that are here. Among them, as we just saw, there is a symmetry that rescales Z's and X's and T's and leaves this geometry invariant. That's part of this structure that's not in the, of course, in Lorentz group, because Lorentz group doesn't have any scaling symmetry. So the generators of this conformal group are, I should just say this here. So the symmetry group here in 5 dimensions is SO42. It's a non-compact group, and this contains the Lorentz group plus special conformal transformations and dilatations. So dilatations are the scaling, sort of which do this, and special conformal transformations are what you know, which do inversions around the sphere. But now they do inversions in this relativistic context.
Here, when you say anti-de Sitter space-time, it looks like you have a particular solution of the gravity theory.
Correct.
Then, what are the degrees of freedom in this theory?
Very good. So since I was only talking about the vacuum of my conformal field theory, the vacuum is a special state. It's a state that preserves all the symmetries. So here, in the gravitational theory, all I have excited for the vacuum is just the gravitational degrees of freedom, in particular the geometry. For every such operator I have, there are of course other operators, these simple words, which I can now make out of these A's and X's. For every such operator, I have a particle that propagates in this gravitational theory. Okay.
Extra fields.
Extra fields, not non-gravity. Well, they will interact with gravity, but they're not part of the gravitational theory. Indeed. So we have this particular theory has an infinite set of such simple words, and there's an infinite set of modes which you can actually organized quite compactly because there's some extra symmetry in the particular theory I'm talking about, which propagate inside this anti-de Sitter space. So the classical theory is gravity plus these fields. So for example, I can pick, I can take this guy, a mu, and I can make a word. So there's some subtlety which I don't want to get into. A mu itself is not a good matrix for me to talk about because of symmetries of my gauge theory. What I can talk about is I can talk about some derivatives on a mu, and I can take, say for example, 2 of them. So this is a nice operator that I can talk about of the kind we mentioned earlier, and this maps to a scalar field in this. So it has, so we can sort of organize these objects by their quantum numbers, and those quantum numbers are inherited by these fields. So this particular quantum numbers of this guy are scalars. So in fact everything is organized in representations of this SO4 too. All my fields.
Is it a different field for every set of local operators, or
it's a different field for every set of local operators. So there's indeed an infinite tower of local operators in this theory.
Yeah. Unlike in standard like electrodynamics or chromodynamics, where you have just finite number of particles here.
Yeah. So the point is that the reason this is infinitely many is because I only told you what's happening in 5 dimensions. I can organize them into a finite number of particles by working in true string theory, which is in 10 dimensions. So if I can organize them compactly, but they are in a much higher number of dimensions. So there's a finite number of particles in 10 dimensions, but when you reduce and talk only about this 5-dimensional picture, you have an infinite tower. Basically, if you sort of think about, say, a particle on a circle. Let's say I have one field on a circle. So if I sort of want to sort of not talk about, if I want to reduce on the circle and forget about the circle, I can talk about modes on the circle carrying some amount of angular momentum. There are of course infinitely many modes which are characterized by the integer value of angular momentum that they carry. So if I go 1 dimension lower, I have infinite tower of states indexed by their particular value of how many times they wind around the circle. But if I go up, there's only one field. So it's precisely that kind of logic that I need to sort of combine this infinite set of fields into a finite set higher up. Good? Very good. So let me say some. So one can do lots of things. One can actually learn to compute these things, but I'm not going to tell you how to compute them from the gravitational side. I want to tell you a little bit about the connection with things like entanglement, and I think it's very easy to draw a picture to say what's going on. Now let's imagine, let's take the cylinder and ask, suppose I take my theory and on this cylinder mark off some spatial region. So imagine for a moment this is not really some matrix theory, but some lattice model, okay? So except that now I have my spins aligned along this circle, and we forget about time for a moment. Now I can mark off this region, and then I can ask, what is the entanglement of this region with the rest of the chain, with the rest of the theory? Okay, so of course in field theory we can do this computation, and a few years ago Tadashi and friends and Shinsei came up with a prescription of how one would compute that entanglement from this geometric picture. Okay. So far I've been talking about how I can reassemble the classical large N dynamics of some matrix set of degrees of freedom in terms of a gravitational theory. Now I'm asking a much more detailed question. I'm asking, can I encode the dynamics, can I encode the information about the entanglement that's there in the vacuum state in this geometric picture? Okay. So yeah, the answer is either yes or no, and we wouldn't be here if the answer was no. And the answer is very simple. You basically solve a very simple problem that I think everybody must have solved, is to solve the analog of a soap bubble problem in this geometry.
Analog of what?
A soap bubble problem, a minimal surface problem. So, so the claim is the following: for this given region, which I'll call A, which in my picture is just a finite arc of this spatial circle. You take this geometry, and in this geometry you find a minimal surface that extends into the geometry, so it's sort of it extends in the z direction, but it's anchored on the boundary of A. I'll draw the top down view. So if I sort of excise time and draw the Poincare disk, so here was my A, and this is the minimal surface.
Minimal surface doing what?
The red part, not the area between the red part and the yellow part. Just the red part.
Just the red part. Yeah. One second.
Yeah.
So this is some surface. I'll call it M of A. Maybe I'll call it. And the area of M of A is proportional to the entanglement entropy of A with the rest of the chain. Okay. So minimal with respect to what? So it's really a soap bubble problem. So this is it. So this is an arc here. It has some length. It's anchored on this wireframe. So you minimize its area.
When you say an arc that has the A is only one dimension, and the M sub A is more than one.
M sub A is also one dimension.
One dimension. So when you say area, you just mean length.
In this case, but if A was,
it could be bigger.
It could be bigger. Yeah. So just to be specific, if in 3+1 dimensions, A is a region in 3 spatial dimensions. Yeah, 3+1 dimensions where the field theory lives. A is a 3-dimensional region. It has a boundary, these points, it's 2-dimensional, and this minimal surface is 3-dimensional. So one has various consistency checks that this works, and I'll show you one of them in a moment, if time permits. But the key point is that, so this is a quantum field theory. So this entanglement of this chain, it's a local theory. The entanglement is divergent in quantum field theory. So SA diverges as the area of the boundary of A, and the same happens for the area of MA, because this surface goes to the boundary of the space-time, it goes to infinity, and because it goes to infinity, or better yet, because of the lengths in this geometry going to becoming infinite as z goes to 0, you get the same kind of divergence from this area as well. So that's a basic consistency check of this proposal, that you have the same amount of same kind of behavior for the entanglement entropy in the local quantum field theory and for these minimal surfaces in this geometric picture. I want to say a few more things about this, but maybe people have questions about this construction.
I actually didn't understand your last sentences. Could you repeat it?
Oh, sure. So, if you have a local spin chain, a local spin system, the entanglement, of course, is local. So,
the entanglement is entanglement is what? Is local?
The entanglement of
this with the rest.
With the rest,
yeah,
is sort of dominated by the edges.
Okay, so you say it satisfies some area law.
It satisfies some area law,
yeah.
And what that area law means is that there's a divergence when I take when I take my lattice spacing to 0, which is proportional to the area of the bounding surface. In this case, just a point, but in more general, there's some domain that demarcates A with the rest. So it scales like the area of that domain. So if I told you that I get the entanglement of this region with the rest from the area of some other surface, I better get that same area law, and I'm saying I do get that because these surfaces end on a boundary, they go to infinity in space time, which is and or better yet, because of this 1 over z squared, the lengths in my geometry become bigger as I go towards z equals 0, and that feature ensures that area of MA also diverges like the area of boundary of A. So there's some basic self-consistency check that one can do, that this is giving the right answer. Because the other checks one can do, but this is sort of the 0th order check one needs to do to make sure that one is talking about the same thing.
So the models that have some logarithmic divergence from the area law on the line, they cannot come from such theory. They cannot have this gravitation.
Okay, so Ashi can answer this question better than me, but so the kind of models where you have logarithmic violations of area law, those are models where you have logarithmic violations not from this kind of local physics, but from the infrared, from some say you have a theory with a Fermi surface. That's an example where you get this violation of area law, but that's because there's some other scale in the problem, right? And that happens when this surface, when you have some deformations not near the boundary, but somewhere in the interior of the geometry, which augments the area. So they can be described, but they're not described by this geometry, they're described by some other geometry. So Tadashi and friends constructed various examples where you can exhibit this logarithmic violations of area law as well. So I wanted to show you one thing which I find quite remarkable in this construction, because it's beautiful, and then maybe I'll stop. So the thing I want to demonstrate is that at least for the simple example, a simple class of states which are time independent, one can prove the strong subadditivity of entanglement entropy very simply from the fact that these are areas of minimal surfaces. Okay, so this is something which is quite nice. So let me open this up, let me talk about let me unwrap this circle and let's draw some regions. So let's say this is A, course, I have two more regions. I have A union B and A intersection B. So here's the soap bubble associated with the region A. And here's one for B. And here are two more. For A intersection B and for the bigger region A union B. Right? So the strong subadditivity result tells us that so we want to see this. We can do this experiment if you have soap bubbles, but it's just as simple without soap bubbles. So I can sort of take these surfaces SA plus SB, or rather the areas thereof, and I can sort of break them up here. Okay, they intersect, but I can break them up. And now, I don't want to deform them that way. What do I want to do? Let's see. No, sorry, I want to break them up this way. So I have SA and SB. I take the soap bubbles, puncture them, and now I realize that I have surfaces that straddle A intersection B and A union B. Right? But these guys, this surface that I have, this deformed surface which I have demarcated here, is not the minimal surface that ends on this surface that comes down here and goes up here. Its boundary is A union B, but it's not the minimal such one that lives there. So its area is clearly bigger than the area of this blue surface, which is the minimal area surface that straddles A union B. Likewise, this surface here straddles A intersection B, but it too is not the minimal area such surface, because the minimal area such surface is further below. So if I puncture these pair of soap bubbles and let them relax to make themselves minimal area, they will relax to this union of these blue surfaces and reduce their area. But then the inequality is clear because I just punctured them, so the areas are, of course, roughly speaking, still the areas of these two things, but the minimal surfaces have smaller area, and you recover the strong subadditivity result. So this is a proof that Tadashi and Matt Hedrick gave many years ago in support of this holographic entanglement entropy proposal, which I think is 2 lines, and we can sort of see this explicitly. There are lots of open questions. In particular, I think I should stop. But one thing I didn't talk about is that we have a proposal with Tadashi of how to extend this to time-dependent situations, and there these type of constructions are much more complicated. So far, we don't have a bulletproof statement that the strong subadditivity state result is satisfied, although we have indications that it is. And then there are lots more interesting recent work trying to, in this holographic context, try to actually associate the notion of geometry itself with some measure of entanglement. I'm happy to talk in private if people are interested in what those statements are, but in light of time, perhaps I will officially pause, and then we can have sort of individual discussions.
So we've had a large number of questions throughout, but maybe there's one or two additional questions.
Why you say that the strong subadditivity may not hold?
No. So in this case, it's true.
Yeah.
So this is what for the simple case where the entanglement is given on minimal surfaces. So and I only described the story for you when the quantum state is time independent. When the quantum state is time dependent, strong subadditivity ought to hold. There's a generalization of this minimal surface story for which this simple proof doesn't go through. Okay, so there's something to check, but there's a more elaborate geometric construction that I can describe for you. But I don't mean to convey the impression that the strong subadditivity doesn't hold. That has to hold from.
One more question. There's such thing like topological entanglement entropy, and they also deal with regions. Yes. I don't know really what is that, but is that related to this stuff or not?
So my understanding of topological entanglement entropy is if you have systems which are gapped and have interesting phase structure in the ground state topology, if you sort of remove all these divergent pieces in the entanglement entropy, there's a finite piece which encodes the notion of topological entanglement entropy. So one can, of course, since one can compute the area explicitly, one can extract that information. It has been claimed quite recently that there are examples where you can actually map this topological entanglement entropy to this particular computation of minimal surfaces in a class of examples. Those class of examples are not, I won't say, they're quite far removed from the class of examples where you sort of see topological entanglement entropy explicitly. They're not basically toric codes or something simple as that. They're still these class of matrix-like theories. Okay, but nevertheless, there's the structure of entanglement in these holographic models resembles the structure of entanglement you see in the topological entanglement entropy context.
Is there some intuitive way to see why we should have this correspondence between entanglement and these minimal surfaces? Like, can you see it? Can you get a sense of it from ADS, kind of the dictionary, or is it somehow independent and just?
No, there's a sort of maybe even pre-ADS CFT intuition for why entanglement ought to have to do something with areas of surfaces. It goes back much earlier to the notion of black hole entropy. And black hole entropy, so black holes which exist in theories of gravity, they have a natural notion of entropy associated with them. And that entropy is associated with the area of some surface, which is the horizon of the black hole. And in fact, Ryu and Takanagi were indeed motivated by that kind of formula for this prescription.
Yeah, the area is the area of the actual
event horizon.
But here it's a different area.
It's a different surface, but it's in some sense, how should I say this? If I put a black hole here and ask you what the thermal entropy of the system was, that's as if I took the entanglement entropy for the sort of maximal size subsystem, and then this surface jumps and sort of straddles the horizon. That's the minimal surface in that context. So in some sense, it's not unrelated, but one has to sort of dot the i's and cross the t's to see explicitly what the relation is. But the intuition is really that there is a connection at the level of holography between areas of objects and measures of information.
Okay, so I guess the holography program is going on until the 11th of?
One more week.
Yeah. One more week. So I guess a lot of people in this room who are not in the quantum information program are good people to talk to if people in quantum information have questions about stuff. So with that, let's thank you.